I'll talk about Verlinde rings and cluster algebras. I will spend most of time to explain certain categories and some maps between their Grothendieck rings. So there are 4 categories appearing here. So this is a finite-dimensional representation category of finite-dimensional representations of quantum affine algebras, and K0 denotes the Grothendieck ring, and this is Q deformation of UG, universal enveloping algebra of G. Here, G denotes simple Lie algebra, finite-dimensional simple Lie algebra. Okay, so there's also representation category, and when we learn representation theory for the first time, maybe after finite group theory, we learn finite dimensional representations of simple Lie algebras, and this is the category of finite dimensional representations. And one of basic results in here is there's an isomorphism between these 2 rings. And this is a bit difficult. This is K0 of rep G hat K. G hat is the affine Lie algebra, and I will explain what these are. So, and this is called the Verlinde ring. There's a ring structure here, and it's a very non-trivial one. And so, because UQG is a Hopf subalgebra of quantum affine algebra, there's a natural restriction map between these 2 rings. And because there's an isomorphism, we can start from, so take an object here, an element here, and we can take restriction map and go use isomorphism. And this is not very well known, but this is a very important surjective ring homomorphism between this ring to the Verlinde ring. So K is a positive integer. So starting from a representation of quantum affine algebra and a corresponding element to in the Grothendieck ring, we can compose these maps. And because when we take restriction, this is a finite dimensional representation. This is finite dimensional representation, and this is finite dimensional representation. But affine Lie algebras, this category consists of integrable representations of affine Lie algebra. These are always infinite dimensional, except the trivial one. So there's a non-trivial branching phenomenon here. So there are now summation. So if you take simple elements here, there's a non-trivial branching, and take isomorphism. And if you map, I will explain what this map is later. But if you take this, so this ring finally has G basis. So this is a free ring over the integers. So there's a finite many basis elements. So any element can be written as a linear combination of this distinguished basis, a linear combination of this distinguished basis. So we can look at the coefficients for each basis element, and the spoiler is this. There is a very interesting positivity phenomenon, and this problem has not been much explored yet. And one part of one reason is, okay, people working on quantum affine algebras usually are interested on this line. And people interested in conformal field theories or topological quantum field theory or modular functor or RCFT usually cares about second line. But so it's a bit hard to think about this composition, but it seems there's something non-trivial phenomenon going on. So because this is the main picture, you should keep in mind. I will just write it down here also. And during my talk, you can just look at this diagram and see which part I'm talking about. G is a simple Lie algebra. K is a non-negative, a positive integer. And okay, so let me begin. So let me begin with a nice image. So this is a sphere, and there is a triangle, and there are some angles given by pi over 2, pi over 3, and pi over 5. And along the side, you can take the reflection. So each side gives a reflection, and this reflection as a isometry of R3 gives this tessellation of the sphere by congruent triangles. And this actually defines a group generated by reflections, and their relations are given by this. And this group is called H3, and this is one example of Coxeter group. And there's an animation how these triangles are propagating along reflections along the sides. So this all covers the sphere, and there's no overlap between each triangle except the edges. And we can see such figures in many mathematics. So this is a picture you can probably see in any elementary mathematics books. And this is a triangle, a tessellation of hyperbolic plane by congruent triangles, hyperbolic triangles. And this is so tessellation of Euclidean plane by triangles. They all define, in a similar way to the previous slide, they all define reflection groups. And there's an abstract notion of this reflection group called the Coxeter group. Coxeter group is defined as generators and relations, and can be specified by a finite set of generators, S, and the relations are given in this form where M, S, S prime are just integers when these two are not equal. And when they are equal, we just assign 1 to the exponent. So this is, so if you put S, we get 1, which means S squared is 1. So this, so this doesn't involve any geometry, but this is an abstraction of reflection groups. And Coxeter groups are classified into 3 types. There are finite type, affine type, and indefinite type. So classical results. So this is a list of finite type Coxeter groups, Coxeter systems. There are A, B, C, D, E, F, G, and H3 that we saw previous slide, H4 and I to M. And probably correspond to dihedral groups. And there's also classification of affine type Coxeter groups. So let's consider in a slightly different context. Cartan Killing in the 19th century, they completely classified finite-dimensional simple Lie algebras over the complex numbers. And the key structure in this classification is something called the root system. And root system is very symmetrical combinatorial object that allows us to constrain the possible structures over the semi-simple Lie algebras. And this data, so this is very symmetric arrangement of roots of vectors in a certain Euclidean space. And this data can be compactly encoded by Cartan matrix or something called the Dynkin diagram. Yeah. Hope most of you have seen Cartan matrix or Dynkin diagrams before. And the relation between Lie algebras and Coxeter group is this. For each simple Lie algebra, we can find a Coxeter group of finite type. And because root system has many symmetries, and actually Coxeter group finite type appears as symmetries of the root system, and we call the group the Bail group. And for each in the previous class, I showed the list of finite type Coxeter groups and affine type Coxeter groups. And for each finite Coxeter group, or finite Bail group, there is a corresponding affine Coxeter group. So to Lie algebra of type A2, the Coxeter group generators and relations look like this. And the affine Coxeter group corresponding to A2 looks like this. So we add one more generator I0 to this, and we need to include some relations involving I0 also. So one of the classical questions asked by Moody is this. So if there's a Lie algebra corresponding to Coxeter group of finite type, is there a Lie algebra corresponding to Coxeter group of affine type? And the answer is yes. And for each affine Coxeter group, we can define an infinite-dimensional Lie algebra whose Bail group is the given affine Coxeter group. And to define all these Lie algebras in a uniform way, it's probably useful to introduce the notion of generalized Cartan matrix. So this is a generalization of classical Cartan matrix for finite type Lie algebras. So this is a square matrix with integer entries, and for diagonal we put 2, and non-diagonal entries has non-negative elements, and ij0 implies iji equals 0. So pretty loose conditions. So we can find many such matrices. And for each such matrix, we can define a certain Lie algebra over C using generators and relations. And so here the index set is I. So for each index, we prepare some generators called EI, FI, and HI. And because this is not necessarily a full rank matrix for 1 to up to its core rank, so up to its dimension of null space, we prepare another generator and can write down relations. This defines a Kac-Moody algebra associated to a generalized Cartan matrix. And it turns out, once we define Kac-Moody algebras in this way, using GCM, generalized Cartan matrix, we can obtain finite type Kac-Moody algebras. And it turns out this is nothing but classical finite dimensional simple Lie algebras. And the types are A, B, C, D, E, F, G. And here there are only finitely many such a list. And there also is another important type, important classes of GCMs. It's called now affine type. Here, this one is not full rank, but its nullity, null space has dimension 1. And it's also some subfamily. One family is called untwist type, and another type is called twist type. So here you can observe for each simple Lie algebra of finite type, we have corresponding affine Lie algebra. So when we say affine Lie algebra, usually it refers to untwisted affine Kac-Moody algebras. So today, when I say affine Lie algebra, it will mean one of these Lie algebras. So for a generalized Kac-Moody algebra of finite type, we can find a corresponding affine GCM. So this is a Cartan matrix for type G2. And this is a GCM for affine G2. So here we have the same Cartan matrix as this, but we have another row and column. It's similar to adding one more generator to the Coxeter group of finite type. Okay, so because this has null space, non-trivial null space, we can define certain quantities using this matrix. So let me first define a few words here. So the null vector of this matrix with first entry as 1. So 1 to 3 is as a column vector, it's a null vector. So these numbers are called the marks. So for each affine Lie algebra, we can define such quantities using the GCM. So comarks are null vector with this normalization of the transpose of GCM. So in this case, it's 1, 1 to 1. So Coxeter number H is obtained by adding numbers appearing in the marks. But there is another way to define Coxeter number as the group, as the order of certain element in the file group. So here the special element is Coxeter element. But anyway, this number coincides with that. And there's also the notion of dual Coxeter number, usually noted by H check. And this is sum of comarks. And when we consider affine Lie algebras, there's a special element, distinguished element. This is central element, which means it commutes with every other element in the Lie algebra and can be found by by taking linear combination of the generators HI using the comarks. So this defines a certain distinguished element in the affine Lie algebra. Am I too fast? Any questions so far? Okay. So let me summarize some basic results on the representations of G and G hat. So let G be a simple Lie algebra. So simple, when I say simple Lie algebra, it means finite type Lie algebra. So here, okay, and G hat is the corresponding affine Lie algebra. Irreducible finite-dimensional representations of G can be classified using R tuples of non-negative integers. And similarly, isomorphism classes of irreducible integrable representations. So integrable is a technical term, but you can just regard this as analogs of finite-dimensional representations. These representations of G hat can be classified by R plus 1 tuples of non-negative integers. A more intelligent way to say this is each integer tuple appearing here is the highest weight of representation, and we call this parameter set P plus and P hat plus the set of dominant integral weights. And this is not deleted, then nothing. Okay, so we saw how irreducible representations are classified. So let P plus, as before, let's be the set of dominant integral weights. So So for each lambda in P plus, so you can just think this as R tuple of non-negative integers, or its highest weight. There's a corresponding finite dimensional irreducible representation V lambda. So, okay, K0 rep G. Now this object, one of the easiest objects in theory of representations, K0 rep G denotes the gross-ending ring in the category of finite dimensional representations of G. And every finite dimensional representations of Lie algebra G can be decomposed into a sum of irreducible representations. So we can take this ring has a G basis, and the basis elements can be, so this is to denote the class of representation. So basis can be parameterized by this set of dominant integral weights, and the product structure on this ring is just given by the tensor product. So once you take tensor product, this it's decomposed into sum of irreducibles, and these numbers are non-negative integers. So if you take any basis elements, can be written again as a linear combination of basis elements, but here structure coefficients are non-negative integers. And similarly, the category of integral representations of G hat so forms a G ring structure. But this category doesn't appear in this picture. Here, I'm talking about G hat, but here I put another parameter K. So, though this is also, this is very analogous to this ring, but we don't consider this as the main object here. So to explain what this is, I need to explain the concept of level of affine, of a representation of affine Lie algebra. So before, using something called comarcs, I defined certain distinguished elements of affine Lie algebra. The central element acts as a scalar or on a irreducible representation of an affine Lie algebra. And this number is called the level. So when you have a highest weight, so I plus 1 tuples of non-negative integers, the level is given by some of these numbers. So here, this is the comarcs that I defined as the null vector of the transpose of GCM for this Lie algebra. So when you have a weight for simple Lie algebra G, so I plus 1 tuple, there is a unique way to define C0 so that this weight has level K. Does it make sense? Because the level is just sum of these numbers, and this is a constant. And once this is defined, there's a unique way to find C0 so that this weight or its representation can be level K. So there's a bijection between the set of finite weights or I plus 1 tuples and affine weights of level K. And when you study affine Lie algebras, it's a phenomenon that it's often very useful to consider collections of representations of the same level. Positive integer here. Yeah. No, of course we can define representations of any other levels, but in my talk, I consider level given by positive integers.
AI check, right? Not every.
Sorry, what's the question?
K is this side.
Yeah, K is just this.
student okay, student okay,
Okay. These are integers.
then it makes the every integer.
Yes. It depends what these are. Because these are integers. These are so
Every k can be represented by some CI. These A, J are A 0 is 1.
yes.
Every k.
Yes, if these are arbitrary, when this is arbitrary number, still you can make this, so this becomes k by choosing C0 in a certain way. Clear? Okay, now consider I plus 1 tuples, which now parameterize the affine weights, dominant integral weights for G hat, now with level k. So this is now a finite set. And K0 rep G hat k, first, this is not yet a ring. This is a G module given with given basis V omega hat, where omega hat is an element of this finite parameter set. But what we want is, so if you drop k, rep G hat K0 just forms a ring, a G ring with infinitely many basis elements. But now there are finitely many basis elements. But there's a natural concept of tensor product for any Chul-hee algebras. So it makes sense for taking tensor product for affine algebras of two representations of level k. But when you take tensor product of two representations of level k, the resulting representation has level 2k. So this is a problem when we want to consider this as a ring. And one of the remarkable phenomena is on this G module, there's another kind of product which preserves the level. Okay. Okay. There are some students here who why this is so. So this is the Lie algebra has this universal enveloping algebra of any Lie algebra has co-algebra structure, and an element center is mapped to this under the co-multiplication. So when we have representation V1 and V2, C acts on C on V1 and identity on V2. This contributes level K. And on another piece, it acts as identity and as level K. So level becomes 2K. So that's why tensor product of two representations has level twice. Okay. But one problem of this product structure, this is very remarkable, but the problem is this is a bit difficult. And I think this is one of the most difficult ways to define multiplication. So let's consider affine algebra G hat and level. And we need now consider something very different from what I have been talking about. Consider fix a compact Riemann surface and choose some points, endpoints. And to each endpoint, we assign dominant integral affine weights of level K. And what we want is to assign certain finite-dimensional vector space denoted by V, G hat, K, X, and P lambda. So I put every choice here. And Okay, there's a way to define such a vector space, C vector space, so that defines various axioms required to define so-called rational conformal field theory. And this, sorry? Lambda zero. What's lambda zero? Yes, G hat. Each is now L plus 1 tuple. Each is a weight. So you choose points, and each point you now attach representation. So similar to what we do in some previous slide of you in defining topological quantum fields theory. So there you assign some vector space to circles, boundary circles on the surface. But here, instead of circles, we choose points, and we assign now vector space, infinite dimensional vector space to each point. Okay. So, and this space is called the space of conformal blocks. And its definition is a bit technical and difficult, so let me skip it today. And in the context of algebraic geometry, this space is also identified with the space of global section of certain line bundle over the moduli stack of quasi-parabolic G bundles over X. Here, G is algebraic group over certain algebraic group over C, whose Lie algebra is finite-dimensional Lie algebra G. So whatever that means, this space has another meaning in algebraic geometry. And the Verlinde formula is an explicit formula for the dimension of this vector space. And it is known that this dimension actually doesn't depend on the choice of points and a number of points. And it also doesn't depend on Riemann surface. It only depends on its genus. And eventually, this formula is expressed in terms of so-called modular S matrix defined for representations of affine Lie algebra G hat. But we don't need explicit formula today. So okay, it depends on the choice of weights, and it depends on level, and it depends on genus. Doesn't depend on the location of points. But it depends on the choice of lambda. So n is already it changes. Yeah. Okay. Now, so far here, I'm talking about this object. So far, this is a G module with finitely many basis elements. One Verlinde's idea was this. We can use this dimension of space of conformal blocks to define a ring structure on K0 rep G hat K. So to do this, we don't need to consider a general situation. So now consider the simplest Riemann surface, which is the genus 0 surface, the Riemann sphere, and consider only 3 points. And to each point, choose 3 affine weights, dominant integral weights. So 3 irreducible representations of affine Lie algebra. And this number only depends on the choice of 3 modules. And because this is defined as the dimension of certain vector space, this is non-negative integer. Then what happens is to the basis elements of K0 rep G hat K, so these are irreducible representations of level K of G hat. We can take product using these integers. Because this is defined as a dimension of certain space, this is automatically non-negative integer structure coefficients. But yes, this notes the dual. dual of representation. So yes. Okay, so one very non-trivial consequence when we define product in this way is this ring now has a commutative and associative it has a structure of commutative and associative ring. Okay, so when you define using product using structure constants, defining something like associativity is completely non-trivial. So to really check associativity, you need to go back to the definition of product. And so it actually involves some geometry, how this really behaves. How this behaves. So here I chose x and n points, and to really consider this kind of properties or structures, as Phil-Sang said in previous talk, associativity is a structure. You need to really consider the moduli space of Riemann surface and with marked points. So change Riemann surface and marked points continuously and see how this behaves and how this behaves under some strange behaviors. And this is a way to explain associativity, but still it's a very non-trivial construction. But once we define this, now just accept this fact. This is a ring, and this has a finitely many basis elements. Then, okay, yes, we can accept that. Yeah. And this product is usually called the fusion rule. And this ring itself is called the Verlinde ring, or it's also called the fusion ring, or sometimes called the fusion ring of WGW model, or sometimes it's called Verlinde ring of WGW model, or Verlinde ring of affine Lie algebra, or fusion ring of affine Lie algebra. Yes. Unit. Okay, so I can explain what unit is. So I explained there's a unique way to lift finite weight to affine weight. So take all 0 here. Then this number must be k, and 0, 0, 0. And corresponding representation plays the role of unit in this ring. Okay. And I think it's still, some people regard this as an open problem to define this product in a more natural way. It's just too difficult, I think. But this theorem, due to Faltings, and Faltings did this for classical types and probably type G2, and Telemann did this for arbitrary types. One can establish the existence of surjective homomorphism from K0 rep G to K0 rep G hat K. And this map beta is defined as follows. Sometimes if it's null, if it's 0, and I define what null means. Null means this weight, this is affine weight, and when it has a non-trivial stabilizer in the affine Lie group, it can be regarded as null, and then its image can be regarded as 0. And otherwise, there's a unique element lambda hat prime. So there's it's one of basis elements, and one problem is you need to put signs. Okay, so when you look at this, probably it's difficult to understand what's going on. So anyway, the point, I will show you some picture in the next slide. And what happens is, so the point of this is, okay, you know how to take tensor product here. So to understand fusion product, this is surjective map. That means take 2 elements here, and take the image. Okay, take an image mapped to a given element and take tensor product and use this map to compute the fusion. So what this enables is you don't need to consider the now conformal block or whatever. You use just Lee theoretic data only to compute the fusion product. So this is a basis, one of basis element here. And lambda check is just the unique lifting into affine weight by adding C0. So although fusion coefficients are defined in a very geometric way, you can essentially, you can use tensor product here with this map. And this map only involves affine Bayer group. So everything now is expressed in terms of Lee theoretic object, no geometry. So this is one picture that I drew last night together with ChatGPT. Okay, this is my first trial. So let me explain what this is. This is for level 3 and type A2 case. So each circle or X denotes the position of integral dominant weights, giving finite-dimensional representations of type A2. And these region is so-called the Weyl chamber for the finite Bayer group. And the fundamental domain for the affine Bayer group is this small triangle. And this is called the Weyl alcove for the affine Bayer group. So this big region, which contains all the weights for G representation, is the finite. It's the infinite Weyl chamber, and there are finally many elements inside this triangle. This is alcove, and this is fundamental domain for the affine Bayer group. So take any element. So in the previous slide, we take arbitrary element here. So take basis element here, and to map into this ring, what we need to do. So say this. Then what we need to do is use the affine Bayer group action to move this into one of these elements, which is a fundamental domain for the affine Bayer group. And this L is the number of reflections necessary to map element from here to there. So maybe, so we need 1, 2, 3, 4, 5, 6, 7, 8. So there are even number of reflections necessary to map elements here to there. And so yellow means it has positive sign under this map. Even number of reflections are necessary. And other regions have negative coefficients under this map. And X denotes where it becomes 0. So really, the fundamental domain for the affine Bayer group, so here the action is actually so-called the shifted Bayer group reflection, which makes the fundamental domain slightly larger. So all this is the fundamental domain. But anyway, you can regard this parameterized basis elements for rep G hat K, and this parameterized basis for rep G. And beta K can be explained by mapping using reflections and moving points here, chamber into the alcove. This is what this beta K does. Okay, now let me introduce the top lines. So let's go back to GCM. Now GCM, associated to arbitrary, so this defines a Kac-Moody algebra. Now fix a quantum parameter Q, which is another root of unity. And UQGA is a Q deformation of UQGA. And this is called the quantum Kac-Moody algebras. And when we consider A untwisted affine type, we call UQGA as the quantum affine algebra, analogous to the the Kac-Moody situation. So UQG hat, similarly, UQG hat is a C algebra defined by generators, EI, FI, but now HI is deformed so that it's exponential of HI. And there are also additional derivation. And when you consider subalgebra generated by EI, FI, and KI, so ignore this, we also call this is a subalgebra, but we also call this quantum affine algebra. And the difference is this doesn't allow any interesting finite dimensional representation, but this allows lots of finite dimensional representation. That's the difference. So this is here has a very rich theory of finite dimensional representations. And so in the title, I put Verlinde rings and cluster algebras, and cluster algebras are relevant to this ring. So similar to the classification of finite dimensional or integrable representations, quantum affine algebra has a nice classification of irreducible representations, but now these are not anymore tuples of integer. These are tuples of polynomials of one variable. And these polynomials are called the Dirichlet polynomials. And for this classification, we need to consider so-called root presentation of quantum affine algebras, but we can just accept representation. For each representation, finite dimensional irreducible representation of UQ prime G hat, we can attach a tuple of polynomials. So this tuple of polynomials plays the role of highest weights. R is the rank of G. Yeah. And Kirillov-Reshetikhin modules are parameterized by three parameters. I is one of index set, and A is a complex number, and M is a non-negative integer. For each triple, we can attach a tuple of polynomials given in this form. And this corresponds to so-called Kirillov-Reshetikhin module. And this is it forms an important family of finite dimensional irreducible representations of quantum affine algebras. And now, this is a bit different story, but this is the actually original motivation to consider this composition. So around the late 80s, some mathematical physicists, Bazhanov, Kirillov, Reshetikhin, Kuniba-Nakanish-Suzuki, and many others working on so-called thermodynamic Bethe Ansatz, arrived at an interesting identities involving the dilogarithm function. And one of a family of dilogarithm identities look like this. For each simple Lie algebra and positive integer level, we can define certain positive real numbers can be defined as a solution of certain equations. And once you evaluate these numbers on the dilog function and take the sum, you get some rational number times this pi squared over 6. And you can see this is a famous number in number theory because it's sum of reciprocals of squares. And the reason is dilogarithm function is actually defined as this way. So when you evaluate this function, when x equals 1, you get this number. And this number has that kind of origin. Anyway, when you have dilogarithm function and certain set of algebraic numbers, and when it satisfies some rational number times L1, this is often called a dilogarithm identity. So the point of this is, okay, you have certain mathematical physics model, and initially it's not related to any conformal field theory or whatsoever, but people in that field produced some method to relate this model to conformal field theory, and this quantity is quite common when you look at literature in conformal field theory or affine Lie algebras. First, this appears in when you look at the modular transformation behavior of string functions of affine Lie algebra representations. So that's one occasion that you can see of these kind of numbers. And another place you observe this number is when you consider these representations of affine Lie algebras as a representations of so-called Virasoro algebra. Then this number, Virasoro algebra representations are parameterized by two numbers, central charge usually denoted as C and H. In this number, C is called the central charge, and this number appears when we consider such quantities. But anyway, from a physical model and using dilogarithm function, you can produce some numbers appearing in conformal field theory. Okay, but once you write down this equation, you don't need TBA anymore, because this is now mathematical statement. Doesn't depend on the validity of mathematical physical method. This is just well-defined numbers, and there's a well-defined function and well-defined numbers. Now it's about proving this identity. Yes? Okay, so this eventually was proved using the so-called Y systems. And so instead of considering these numbers, we consider a functional version of dilogarithm identities and specialize it. But I don't think there's any explicit way to prove such a functional equation using only 5-term relations. But when I talk to some experts in this area, some people regard this is already known, and some people say it's not known. So I decided not.
So you're saying classical, you're talking about quantum cases.
No, I'm not talking about quantum. So his question is about whether we can write down this using.
The Y system is a quantum system. Yeah, okay, classical. And then you.
Okay, so our Y system. Y system, I can say it's a classical. For me, it's just a recurrence relation. So there's nothing quantum or. Yeah. Okay.
Why is it 2 index?
Sorry?
Why is it 2 index M and I?
Why? It's a way of defining this equation. Okay, so I didn't explain what these equations are. So, yes. Yeah. Okay. And one of conjecture, or the conjecture by Kirillov and Kuniba-Nakanish-Suzuki was really now we can go back to representation theory. These numbers appearing in dilogarithm identity can be obtained explicitly by computing quantum dimensions of Kirillov-Reshetikhin modules and take this combination. So what is quantum dimension? Quantum dimension is not something very mysterious. When you consider UQG, when you consider representations of UQG or RepG, there's a highest weight for the representation. And this is very similar to Weil dimension formula. This is product of positive roots and positive roots. And what happens is when you take k to infinity, this number, you can actually remove this and sign. And what's left is the Weil dimension formula. So by taking k to infinity limit, you get dimension of representation. So this is some deformation of dimension. But both 0. We have 0 and 0. Yes, it's 0 over 0. So you take limit and some finite quantity appears. And that's the dimension. Okay. Okay, so for each G and choice of level, we define some quantities like this. So let me show you an example. So this is an example type D5 and level 4. If you compute the quantum dimension of Ki modules, so this is for, so there are 5 columns because there are 5 vertices in the Dynkin diagram. If you compute the Dynkin, if you compute the quantum dimensions, you get some positive numbers starting from the first law, and it starts increasing and eventually start decreasing and come back to 0, and there are some zeros appearing, and you see some numbers reappear here. So, and you can use these finite many positive numbers to consider the dilogarithm identity. The point is, okay, when we compute the quantum dimension, if lambda is very big, this number can be big. That means the sign can be the sign of something can be negative. So quantum dimension itself is not necessarily positive. So but for dilogarithm identity, we need positive numbers. But this positivity is not obvious from the definition. So this was the conjecture they wrote down in the work on dilogarithm identities. And what I found when I saw it is, actually we can use this now. What happens is, here they consider quantum dimension in objects by considering decomposition of Kirillov-Reshetikhin modules and by taking quantum dimensions. But quantum dimension actually factors through all this map. And what happens is, if we can prove positivity, so this has a distinguished G basis. And when you have positivity here, positivity of quantum dimension is automatic. And what happens is we can actually prove positivity on this level, not just numbers.
So your positive here is K and K for the unit K?
Sorry?
So your positivity here is your positivity on quantum dimension and K also.
No, for each positive integer K, we have, so this is for each choice of G and K. Okay, what happens is, okay, so if you take Kirillov-Reshetikhin module and different level, you get bigger K has longer positive numbers, but eventually it becomes 1. And smaller K becomes becomes 1.
And your K is the finite, but
yeah.
You would get some constant K as K goes to infinity.
So when you take K infinity, you just get dimensions eventually. But positivity anyway is for given positive K, this positivity is non-trivial. That's what I mean.
That's what I think.
Yeah.
I
Okay. So my conjecture, and so this is Kirillov and Kuniba-Nakanish-Suzuki. Here, I just abbreviated. Okay, so I'm out. Okay, so what I found is actually we can consider positivity in this level. So for Kirillov-Reshetikhin modules, so here, Kirillov-Reshetikhin module lives here, and we take all composition, and this is distinguished G basis, and what happens is for certain parameters, for certain M, we get positive elements here, and it becomes 0 at certain line. Oh, sorry, this is, no, ignore this 0. It's positive, and eventually it becomes a unit element in the Verlinde ring, and at the next line it becomes 0. So I will show you an example. So previously I showed quantum dimensions, but here is now, there are some Kirillov-Reshetikhin modules. So level is 4, so there are up to this Kirillov-Reshetikhin module, we expect positive quantum dimension. And what happens if you take restriction, it decomposes. Now we have objects here. Obviously, it has non-negative coefficients. But beta k now introduces some signs, because as I showed in previous slide, depending on the number of reflections necessary to move them into the alcove. But what happens is there are some nice cancellations, and eventually everything cancels, and only positive coefficients remains. And from here, we can explain why positive numbers appear here. But this was the status of many years ago. But this was a bit unsatisfactory because, okay, we can consider arbitrary elements and take composition. But what it does is positivity phenomenon, I only considered Kirillov-Reshetikhin modules up to certain parameter. It's somewhat unnatural. So I occasionally thought about this problem. So the problem is this: what's the right domain for the positivity problem? For certain Kirillov-Reshetikhin modules, this is positive. But I know some Kirillov-Reshetikhin modules vanish here. So positivity doesn't hold for arbitrary element. It's some subset of elements here. And this is where this so-called Hernande-Leclerc category. So Hernande-Leclerc defined a certain subcategory of UQG hat in 2010. And interestingly, this is closed on the tensor product. And its gross-ending ring has a cluster algebra structure. And especially, and their category is parameterized by an integer. And especially this gives a so-called monoidal categorification of cluster algebra of finite type. And its initial seed are given by Kirillov-Reshetikhin modules. And last year, sometime when I was attending some seminar, and Jianrong Lee was talking about this category and was talking about, of course, about his research. And at that time, I just thought probably CL might be the right category for the domain of this positivity problem. That's how we studied this project. And so for any G and an integer, we can actually define a subcategory here closed on the tensor product. And gross-ending ring has cluster algebra structure. And what we expect is now, instead of everything, some have negative image and some has zero image. So instead of considering everything, we can write down CL here. And then we can say cleanly, not just Kirillov-Reshetikhin modules, we can say this probably is positive. The problem now looks much cleaner. So we can prove some evidences. So first, for some types, and sometimes it's just computational, but we can check every V in this category has positive image in the Verlinde ring. And another evidence is for classical types, which where this conjecture is known, we can check every V in this category has positive quantum dimension. We can take this as an evidence why this positivity. So take any object here and consider this composition. And we expect the positivity here. So let me show you one computational example. So this is E6 case, L equals 1. This was done a few weeks ago. There are 6 cluster and 6 frozen variables. So we denote them by x1 to x12. And one of the clusters looks like this. So let me explain. Each x variable corresponds to a certain Kirillov-Reshetikhin module. And when you consider this product and sum and division, interestingly, this categorification of cluster algebra gives this rational function correspond to a certain module. This is very interesting phenomenon. You cannot divide module by a module unless this is a submodule. But this is not necessarily a submodule. But anyway, you can divide it in a certain way, and then you get objects in the category. So what happens is this. So this is now, this just denotes the rational function that I showed. And this selected region, it's the decomposition of corresponding module here into in here, K0 rep G, Q, or this because this is isomorphic. And okay, so what you can see is this is a very big finite dimensional representations of G or UQG. And there are this multiplicity are very, very large. But when you take beta K, there are lots of cancellations among each other, and this is the result. There are only 1, 1, 2 remaining as coefficients. And this proves non-negative coefficients in this case. So one of the difficult part when you consider this is, so we need to consider the branching of this module as a module of UQG, but there's no known rule for general modules. So computationally, but for Kirillov-Reshetikhin modules, we can do decomposition well. But what cluster algebra structure does is everything essentially can be written in terms of Kirillov-Reshetikhin modules. That's one way to think about this. Although this category, when we consider this category, this treats every module in an equal footing. But in reality, Kirillov-Reshetikhin modules are somehow we can handle very well. And other modules can be accessed by using Kirillov-Reshetikhin module in a recursive way. And that's what cluster algebra does. So we can obtain this kind of decomposition, and we can eventually look at the image. And this is the result. This kind of phenomenon happens. The only nice cancellations and only positive coefficient survives. But the problem is, I don't know why this kind of positivity happens. And yeah, I will just give this as a problem to you. Yeah, let me stop here.